Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. I see all kinds of interesting questions here. Let's see, a few saved up here. There's one from Erin. As Wolfram Language grows, will the number of lines of code ever shrink? What would cause such a trend? So first thing to say, Wolfram Language is the big software system that I've been building, well, kind of directly for 35 years and in some ways for 43 years or so. It's our computational language to kind of represent everything in the world computationally, and it's used by lots of people. What is it ultimately? Well, I haven't counted recently, but I think it's probably about 50 million lines of code. That's the internal code that defines this language. It's the thing that defines all the things that compute, the distance to the moon, or compute something about the color distribution in some image, all those kinds of things. Maybe that estimate is actually too low. Maybe it's closer to 100 million. I'm not sure. But what actually is the internal code that implements all of those things? When you type something like edge detect in Wolfram Language, that the actual code that runs is this big chunk of code that tries to figure out all the different methods it might use to deal with all the pixels in your image and do all those different kinds of things. Very often there are sort of meta algorithms where you'll ask it to do one particular thing, like do some machine learning operation. It has many different ways it might do that, and it has to select for your particular problem which one to use. So there's lots of different pieces like that. Okay, what is that code? Well, some of that code is Wolfram Language code. So in other words, what it's doing is it's saying, there's a function. Let's say it's a function that's nesting other functions or something. You can write that function in terms of other Wolfram Language functions. So in other words, you can write a new function in terms of existing Wolfram Language functions. And over the last probably 20 years, most of the new code that's been added to Wolfram Language is written in the language itself. Some of it, the very low-level code, is written in the C language, or actually an extension of the C language, which is a language that gets really much closer. It's a low-level language that gets kind of close to the underlying operation of the hardware of the computer. Now, C language is a compiled language, so from you write your code and then you run the compiler program, and it turns your code into raw machine code that can be explicitly run directly by the CPU of your computer. In Wolfram Language, the most direct way that things work is if you've got that thing that says, do edge detection or something, edge detect, that will be a piece of code which will be then just run at that time. It will already have been turned into the form that needs to be to run. It's not something where if you build a piece of code in Wolfram Language, the most standard operation is that piece of code will be gone through at the time when you ask it to run, rather than will be initially turned into machine code as a separate compilation step and only later actually run on your computer. Okay, so what determines the length of the code one has? Well, the thing that has made the code of Wolfram Language as short, and maybe 100 million lines doesn't seem short, but as comparatively short given the functionality of the language as it is that the building blocks that one can make use of in that code are very high-level building blocks. So whereas in a low-level language, you might say, I want to move data around from here to there, I want to make this loop that adds this value to this and does that and then does that and so on. There's a lot of code you have to write to specify what you want to have happen because it's very low-level code. In Wolfram Language, there's things where there's just something that represents, I don't know, edge detect an image, take that image and change the colors in it and so on. Those are just single commands. In some lower level language, those will be 10, hundreds of lines of code, or something that computes, I don't know, the shortest tour going around a bunch of points on the surface of the Earth. There's a lot of different sort of moving parts that are needed to make that work, but in Wolfram Language, it's just one command. So what happens is the whole idea of Wolfram Language is to make a language where it provides building blocks that are as high level as possible, building blocks that sort of do the operations that you might think of doing computationally and do them in a way where what you have to specify is as minimal as possible. So given those building blocks, each brick kind of packs a lot of power. And so as you build these programs with these kind of these sort of mega bricks that Wolfram Language provides, you're building a program that can sort of correspond to a very tall tower. So the higher level the code, the more each individual function in the code does, each built-in function in the code does, the more functionality you're going to be able to get for a smaller amount of code. And the lower level the language is, the less functionality you're going to get per line of code. So what might be 1 or 2 lines of Wolfram Language code might be 3,000 lines of C code, or at least hundreds of lines of C code. And so the higher level language, the shorter the code. Now, how does that work in terms of the code of Wolfram Language? Well, the thing is, what we always try to do in building Wolfram Language is when we see a piece of computational work that is repeatedly done and that we can sort of specify a name for, that becomes a built-in part of Wolfram Language. So for example, what's a good example recently? Oh, I don't know, I can think of, I don't know, subset replace, maybe not the least obscure example. But it's a thing that you can write subset replace as a collection of perhaps, I don't know, 3 lines of code or something. But it's something where you see that particular sort of idiom for code repeatedly. And so we sort of turn it into a single word, subset replace. So when you come back to use it again, now in a new version of Wolfram Language, all you have to do is say subset replace. You don't have to give those 3 lines of code. It's kind of like in a human language, before there's really a word for something like a live stream, for example. Before there was a word for live stream, you might have explained that of, oh, I'm going to connect to the web and we're going to send this video and many people will watch it, and it's a whole multi-sentence explanation. And then eventually, when that's commonly enough used in a human in a human language, excuse me. Sorry. when some kind of statement is commonly enough used in human language, then oh boy, then you end up developing like a single word that represents all those things. The single word live stream that stands in for that whole sort of block of words that you might have used before. And that's what we should try to do in Wolfram Language as well, is when we see this kind of repeated block of computational work, we replace it by kind of a single word that represents that whole block. So if we then come back through and we say, look at all this code we wrote before, now we have a better way to specify those same ideas using this kind of shorter, using this new building block that we've made, which makes everything shorter. So the usual term in software engineering would be something like refactoring the code. It's sort of a new way to do the same thing with code. And it's something that we do a certain amount of. We come back through and we change code that was sort of written a long time ago in this rather complicated way. And now we have some function that just does the same thing, but in a much more compact way. Usually when we do that, that single function is a little bit more powerful than the block of code that you explicitly wrote before. It has, because we've just got one place to implement this, you can sort of put more effort into dealing very efficiently with all the different cases. It's much better to have that single encapsulated, sort of well-implemented function than to have all that explicit code that you wrote. Okay, so that's one trend. Another trend is that we are steadily getting rid of all C code that we had in the code base of Wolfram Language. And part of the way that we're doing that is we are building a new generation of compiler for our language. So we're able to go from those specifications of Wolfram language down to, in the end, actual raw machine code. So we can take these very high-level representations of things and compile that through some intermediate language down to machine code. And so the version, so we're replacing C code with essentially just pure standard Wolfram language code, although in order to make it as efficient as possible, we're giving hints in that Wolfram language code that tell the compiler things about how it should compile that code. So that's another thing which over time, over the next few years, will probably make vast swaths of the source code of Wolfram language much shorter. So it's really that kind of refactoring process of now we've got new building blocks with which to implement what we're doing that will make the code tend to be shorter. And generally, it's better to have shorter code. It's better to have code that is made in these modular pieces where there's one piece here that is reused over and over and over again, and where that piece is just implemented once, rather than sort of semi-copies of that piece implemented in many different places. The reason that's a good idea is because let's say that you want to improve that piece of code. Well, you only have to improve it once. You don't have to go search for, oh, did I do something like this in these different places before, and so on. Now, one thing that can happen to code, and a reason to kind of do that kind of refactoring, is it's sort of a strange thing. You might think that software, code, once it's written, it's there for all time. But it isn't really true in practice. Code has this terrible habit of rotting, as people will say. What does that mean? What that means is you have a piece of code and it does a particular set of things. And then somebody notices, oh, what about this weird case? Maybe we should put in a little extra piece of code to deal with, if this happens, then do this special thing. And then maybe somebody else notices, oh, you could make this more efficient by breaking that into lots of different cases, but then there's one case that gets handled differently, and so on and so on and so on. And pretty soon, over the course of years, as people make these little tweaks to a piece of code, the code gets more and more and more complicated, and it gets more and more to the point where nobody can really understand in detail what it's doing. And so that's the sense in which sort of code has this habit in practice of sort of rotting. And that's a thing where if you come through and you say, okay, we're going to take the basic functionality of this piece of code and we're just going to re-implement it using the sleekest, best new capabilities and functions that we have, you'll usually come out ahead. It'll usually be a better thing to do. You'll remove sort of bugs that developed from all of that tweaking that got done. You'll bake it using more maintainable building blocks, but you only have to kind of service them in one place rather than dealing with all those different places and so on. So anyway, that's a few thoughts on shrinking of code. It's really a feature of, I would say, high quality software engineering, that there is a gradual rate of doing that kind of refactoring of code on a time scale of 5, 10, 15 years, whatever it is, that one sort of refreshes the code so that one kind of deals with this kind of this collection of tweaks that build up. Sometimes in practice in the computer industry, there are things that sort of force that refresh, like there's new kinds of computer hardware, like one's gone from 32-bit computers to 64-bit computers, and some things have changed. Actually, in our code base, that affects almost nothing. We have from the very beginning, we had sort of set the code up so that it basically just has one file that specifies all those kinds of things, like, is it a 32-bit machine, is it a 64-bit machine, and everything else kind of flows through and computes what it should do based on that. But sometimes there are these drivers from the way that the computer industry evolves that sort of force a relooking at code. Sometimes for us, it's that in a particular area, we realize there are different things that can be done. We want to add a lot of functionality in that area. Or sometimes there are new algorithms that we've developed or that other people have developed that are relevant for that area and need to be implemented. All right, let's see. Gosh. All right, a few questions here. There's one from Frost here, talking about scientists are trying to elucidate the origins of life on Earth. Current focus is exploring the RNA world. saying that occurred 4.5 billion years ago, that seems a little long ago. I would have thought it was a little less time than that. Could there have been things like dimension fluctuations back then? How different could the universe have been back then? The universe is steadily expanding, and there are features of the universe that certainly change over time. For example, right now, the radiation that's left over from the Big Bang at the beginning of the universe, it has a temperature throughout the universe of 3 degrees above absolute zero. Back a couple of billion years ago, that temperature will have been somewhat higher, like 10 degrees above absolute zero. What difference that will have made sort of here on Earth, I doubt it made very much. I think by the time the solar system was formed, sort of the universe would have been locally, at least, not much different from the way it is today. I mean, there are clearly things that happen in our galaxy over a time scale of billions of years. I don't think the sun has not gone around the galaxy. The sun orbits the center of the galaxy. I think it's only gone around maybe 50 times since the sun was formed, and 5 billion years ago or so, and which is about, the universe is maybe 14 billion years old. So the sun has been around maybe a third the time the universe has. But things will have happened in our galaxy. The black hole at the center of our galaxy is certainly getting bigger. If we lived near that, then maybe there would have been more obvious change. But as it is, we live out in one of the spiral arms of our galaxy, pretty far away from those kinds of things. So the question is, in terms of our theory of physics, there are things that happen in the very early universe, like the fact that we have 3 dimensions of space that we experience today. We think that in the very early universe, there were many more dimensions of space, and gradually sort of things cooled down so that we have the number of dimensions of space that we have today. And we expect that in the sufficiently early universe, there will have been kind of dimension fluctuations. Instead of us having 3 dimensions of space, we'd have like 3.01 dimensions of space and so on. Those dimension fluctuations, I would suspect, don't know, but I would suspect that they're pretty much gone by the time the sun is formed and so on. Perhaps not. And perhaps the thing to understand is that there's plenty in our universe that's left over from that long ago. For example, there are photons, particles of light, that have been traveling through the universe ever since, well, basically for 14 billion years. Ever since the beginning of the universe, they've just been traveling. They didn't hit anything. Finally, we might detect them. And it's like after 14 billion years flying through the universe, splat, the photon hits, our eye or a detector that we have in space or something like this. So, but there are plenty of things that get left over from the early universe, whether it's photons, neutrinos, there might be some gravitational waves, things like that. So there are the kind of things like atoms and so on tend to be of much more recent lineage that we see in the universe today. Actually, maybe that's not correct. Out in interstellar space and intergalactic space, there are certainly hydrogen atoms that really nothing much has happened to that hydrogen atom for most of the history of the universe. If you're in the middle of a galaxy, then all sorts of things can happen to those hydrogen atoms. They can be in stars, and they can be have fusion between other hydrogen atoms and stars, all those kinds of things. But so I don't think that those purely sort of physics and cosmology effects are probably very important for the things that happened in the chemistry of the early Earth that led to the formation of life on Earth. There are things people wonder about. Like, for example, one feature of life on Earth is there are some molecules where you could have kind of a molecule that has kind of a right-hand rule for how a certain arrangement of atoms is relative to other atoms, or a left-hand rule. It's kind of the atoms can be arranged both ways round, and there's sort of a chirality, a handedness to the molecule. Sugar is an example of such a molecule. And in a sense, the sugar that we normally encounter in biology is right-handed sugar. The particular atoms are arranged in the way that sort of corresponds to something like sort of one thing sticking out that's like a thumb, and the other atoms arranged like the fingers on one's hand when one curls it up. When you just start making sugar from its ultimate ingredients in a lab, you'll get equal amounts of left-handed and right-handed sugar. But in life on Earth, it's all right-handed sugar. And so one of the questions, which is something that people look to the very early Earth to answer, is why did life end up getting, all things that were sort of one chirality, one-handedness, all its molecules sort of be the right-handed version rather than the left-handed version. And there are some theories that has to do with some details of the way that cosmic rays, particles, protons particularly, coming from the sun operate, and the kind of thing that happens in radioactive decay, where it turns out that this handedness, things are not equally handed in radioactive decay. The main reason for that is that radioactive decay, so-called beta decay, that involves essentially neutrons and a neutron in the nucleus of an atom kind of decaying into a proton, an electron, and an antineutrino. So it turns out that neutrinos are basically always left-handed. Antineutrinos are always right-handed. It's something where there isn't sort of equal-handedness of the neutrinos that are produced. They're always left-handed ones that are produced, essentially. And that causes the electrons that are produced in beta decay to have another kind of handedness. And when those things interact with chemicals in chemical reactions, there will be a slight tendency for the right-handed sugars to win out over the left-handed sugars. And over the course of time, and as biological evolution takes root, eventually the righties get rid of the lefties, so to speak. As a left-handed person myself, about 10% of humans are like that. I hate the idea of kind of the right-handed everything molecules sort of taking over the Earth, but so it goes. But anyway, I think those are some kinds of places where sort of raw physics interacts with the kind of the biochemistry of the formation of life on Earth. In general, the process of how things were formed in early life on Earth, there's a lot that's not known about that yet. But one of the things that seems to be the case is that what's kind of important is these chains of chemical reactions that are kind of cycles of chemical reactions and that's sort of a place in which some kind of memory is retained, because it's kind of like molecule A turns into B, turns into C, turns into D, turns back into A again. And that kind of, the existence of that kind of loop is some form of kind of simple chemical memory. And that seems to be an important thing in kind of some features of the way that what turns into life as we know it now, with its very long-term memory that's stored in DNA and in genomics and so on, the way that arises. And there's sort of many steps from those kind of sort of loop reactions, so to speak, to the place where we actually get things like DNA, and we get these sort of permanent storage in molecules. And perhaps there were surfaces like solid surfaces like clay, for example, which could have been sort of imprinted by these various kinds of chemical reactions and been another kind of way to store the memory of things in life. Because one of the characteristics of life is that it sort of progressively builds, in a sense that you have you have some kind of chemical reactions, and then you can kind of take those for granted, and then you add more and so on. It doesn't always, I've talked about this in other cases, it doesn't always get really more complicated. It's a little bit like the code I was talking about earlier. I mean, life biology does refactor things from time to time. As things get super elaborate, eventually it'll turn out, well, that incredibly elaborate, weird sort of horn-shaped thing that's on the heads of these kinds of organisms, that just wasn't that important. And why spend all your effort doing that? And every so often it gets tangled up in a plant somewhere, and that's a bad idea. And so that thing stops being selected for by biological evolution and disappears, and you get sort of the refactored organism where that's simpler. And so that happens in biology. The code gets simpler, so to speak. Maybe not the actual DNA, although that does also get simpler in different organisms. We're certainly not the organisms that have the longest DNA sequences of all organisms. So that kind of thing happens there. But yeah, I don't think that these kind of effects that come from physics and cosmology are likely to have had a big effect on directly on the formation of life on Earth. I mean, people talk about, for example, the form of our solar system, which still looks a little bit unusual relative to the typical exoplanet systems that have been seen, but that may just be a phenomenon of the only exoplanet systems we see are ones that have a particular kind of configuration of planets, because those are the things that we are able to detect with our technology today. But it could be the case that some kind of external sort of astronomical phenomena have been important in determining the way that our solar system is arranged. I mean, for example, it could even be the case as the sun has gone around orbiting the galaxy 50 times, it kind of, as it does those orbits, it goes through these different regions of the galaxy, and maybe every so often it goes close to other stars, and maybe when it gets very close to another star, we're not very close right now, 4 light years is the distance to Alpha Centauri, the nearest star other than the sun, but I don't know how long it will be, but in some number of hundreds of millions of years, will no doubt go close to some other stars. And if you look up the kind of the astronomy textbook of 50 million years from now, or 50 million years in the past, it won't say Alpha Centauri was the closest star to the sun. And there will be times in which there are stars that get pretty close to our solar system. And when that happens, the gravity of those stars may perturb the planets that are in our solar system. And that might have been an important effect in determining the final configuration of planets. And that final configuration of planets is important in the fact that, the temperature of the surface of the Earth is roughly this, because it's roughly this distance from the sun. And it's maintained in a stable orbit by the fact that, there's this very big planet, Jupiter here, and so on and so on. It's a whole collection of different kinds of things. And perhaps even the fact that there were asteroid impacts on the Earth. You have to have an asteroid belt to have asteroid impacts. And the fact that there's an asteroid belt in our solar system, we don't know for exoplanet systems yet. Solar systems around other stars, we don't know that yet for them. The fact that there is an asteroid belt here might be for some detailed reason of some planet got, collided with another planet or didn't form into a planet because of the effect of the gravity of some other star as the sun orbited the inside the galaxy. So there are complicated kinds of things like that. Let's see, there are questions here, so many different questions. Another one from Aaron. Why are small children able to spin around so quickly without getting dizzy while adults become nauseous? Okay, it all has to do with our inner ears. And these things called ooliths, spelled O-O-L-I-T-H. So how do we know which way is up? Well, it's really important that there's gravity that defines which way is down, so to speak. And none of the things I'm talking about work if you're weightless in space, if you're in zero gravity, just sort of floating without a definite pull direction to gravity. But when there is a definite pull direction to gravity, the question for your brain, our brains, is which way is up, and so on. And the way we determine that is kind of clever. Inside our ears, there are these things called semicircular canals. There are basically these little loops that are made from bone, and they are in 3 different directions. They're kind of in the X, Y, Z coordinate directions, 3 loops. And inside those loops are these little tiny things called ooliths, which are essentially little stones. And when we are and those, as we turn our head, for example, those stones will kind of move around, they'll slide around inside those semicircular canals to the place where they are at the lowest point, for example. If we're accelerating, if we are kind of being spin around, I should say that's when you're standing still, it's just determined by the force of gravity, and the ooliths will kind of adopt the lowest point in those semicircular canals. If you spin around, it's like the centrifugal force. Okay, so you spin around, you take something and you spin it around. It's on a string, let's say. It tries to pull outwards. Why is it trying to pull outwards? Well, if you left it to its own devices, it would like to just go in a straight line, kind of a basic law of motion, Newton's second law, Newton's first law actually, is if that things that are just in motion in a certain direction will just keep going in that direction and will not deviate from that direction. When there's no gravity, when there's no forces acting on things, that's what happens. Things just keep going in a straight line. So if you're whirling that thing around your head, you have to stop it doing what it otherwise wants to do. It wants to just keep going in a straight line. But in order to stop it doing that, you have to continually exert this force that is pulling it in to prevent it from going in a straight line. And what you have to, if it was going in a straight line, there'd be no acceleration to its motion. It would just be going at a certain fixed speed, fixed velocity, and you wouldn't, but acceleration is the change of velocity, the change of speed, or the change of direction of motion. And so what you're doing when you keep the thing going round in a circle is you keep on changing the direction of motion, so you are keeping on accelerating things. When you accelerate things, there is this force that tends to make things, because things want to sort of keep going in a straight line, you have to exert a force to prevent them doing that. End result, kind of obvious in its own right, those little ooliths in your inner ears, if you spin around, they'll sort of go to the outer part of those, the sort of the semicircular canal, just like that thing that you spin around your head on a string would go as far away as it can, sort of in that circle as it's spinning around. So what will tend to happen is, as you accelerate, as you spin around, for example, those little tiny rock-like things in your inner ears will try and get to the place where they are sort of maximally spun out, so to speak. Okay, that's all fine. It's pretty gooey inside one's inner ear, and I think as one gets older, it gets gooier, and so this sort of the easy sliding of these ooliths through the inner ear tends to be something that gets more difficult, or can get more difficult as one gets older. And well, this question of and so this issue of actually, it's not quite explaining the dizziness question, but let me come to that in a second. So one of the things that can happen, you can get an infection of the labyrinth, as it's called, in your inner ear. And when that happens, you can get into a situation where you where these ooliths get stuck because there's infection in there, and they can't. There's something. I don't know what it is, bacteria maybe. I'm not quite sure actually. That is inside that semicircular canal. Anyway, it gets gummed up in some way. There is this very weird maneuver that has a name which I now forget, that one can use if the ooliths in one's ears get stuck in a certain position. It's a weird kind of exercise that involves kind of spinning oneself around and turning around this way and holding one's head that way and turning one's head this way. And essentially, it's like one of those puzzles where you're trying to get the piece out of the puzzle. You're trying to get the oolith out of where it's been wedged in your inner ear. And it's really quite a bizarre effect. I happened to me once, I got some kind of weird thing where I was getting some weird sort of dizziness, and I try this strange maneuver. I'm very bad at kind of imitating instructions, but if you find a video on the web or something of how to do it, you can learn that. You do it once, and oh my gosh, you're not dizzy anymore. It's really a weird thing. Okay, why do people get dizzy? What's going on there? I think the main thing that's happening is that you have a mismatch between what your eyes see about how you're moving your head and what you sense in terms of the motion of your head. And I think what happens is that that kids where these ooliths are running all nice and smoothly and things, as they turn their head, their sensation of where their head is oriented agrees with what their eyes are telling them about where their head is oriented. So all's good. But when that gets out of whack, when there's a delay, for example, between what the sensation of the orientation of your head is relative to what your eyes are showing. It's kind of running your brain really fast, trying to figure out what on earth is going on, and that shows up in being dizzy. And I think sometimes when you're dizzy and you spun around, it's kind of like you feel like you're keeping on spinning, and that's an effect having to do with your inner ear and those ooliths in your inner ear somehow continuing to move, and they hadn't finished their motion and gotten to where they were going to. They're sort of still moving even after you're not moving anymore, because they just have some viscosity to motion, I think, at least. Now, one of the places where this shows up again is with virtual reality headsets. And I have to say, I actually have not worn one in a little while, even though the metaverse is big. I kind of got put off, so to speak, because I've used these things many times. And one of the things that happens is I get a kind of motion sickness when I use them. And the real thing that is the difficulty for virtual reality systems is what's happening is there's it's trying to show you, you have a head-mounted display, and it's trying to show you, as you turn your head, you start to see a different view. And that has to be done as a piece of sort of computation that, you turn your head, the headset senses the orientation of your head. It has these things called MEMS, which are kind of semiconductor devices that sense acceleration and from that sense orientation. And so the headset is sensing the direction that your head is in, but then it has to sort of repaint the screen to show you what that scene was. You're looking straight ahead at that dinosaur or something, and you look to the side and there's another dinosaur about to attack you there, or whatever it is. But it has to show you that part of the visual scene that would correspond to what you would see if you turned your head in that way. And the question is, how quickly does it do that? Or does it have a delay in doing that? And even the slightest delay there causes all kinds of problems in our brains and visual perception and so on. And for me personally, at least the up until the 6 months ago version of VR headsets, I can only be in them for 5 or 10 minutes, because beyond that, I get terrible motion sickness from some kind of thing that my brain is doing or not doing or whatever about the timing of, I think, about the timing of how the actual image lines up with the orientation of my head. And yeah, the other factor here is that I can feel in my inner ear, in this semicircular canals and ooliths and so on, I can feel what the orientation of my head is. And if things don't agree, if what I see in the virtual reality headset doesn't agree with what should be the case from the orientation that I can feel for my head, I get very confused and I get very motion sick. So let's see. So question from D0 here. Are there parts of our body that we evolved away? Do we still need the appendix? There's a terrible tendency in many areas of science and in medicine to say, oh gosh, we don't know what that does, so we don't need it. This is, unfortunately, it's very hard to know for sure what something does. I mean, sometimes it's obvious, but sometimes it's not. I mean, there are even parts of the brain where people, even 50 years ago or so, were like, that doesn't do anything useful. You can just remove that part and nothing bad will happen. Turns out that wasn't true. It wasn't obvious that nothing bad happened because it wasn't a part of your brain that actually made you be able to move your hand or something like this, but it was a part of your brain that was important in sort of aspects of personality that were a little bit harder to measure. So this idea of, it's not something you need, one can take it out, is I think fraught with difficulty. As far as the appendix is concerned, it's this kind of strange knob on the side of the intestines, and it's a place where one can be unlucky and get something stuck in it, and then it can get infected, and one can have appendicitis, and that's bad. But why is it, quotes, why is it there? Is it there just because our intestines evolved from the intestines of of lower mammals and things like this, and it kind of never got taken out? Not clear. It's not clear. There might be things, for example, there's increasing evidence that the flora, that the kind of bacteria that live in our gut are important for providing all sorts of things that relate to our overall health, for sort of tuning up our immune system, for interacting with the rest of our bodies in a variety of ways. And it could be the case that that something like the appendix, it's there because, oh, you actually want some kind of pieces of benign bacteria to hang out there and, sun themselves for a while rather than getting flushed through the whole intestinal system or something like that. And I'm just making up that explanation. But in other words, it's not obvious, when you see something like that, and gradually you learn that the microbiome of bacteria that live in our gut are much more important than people assumed in the past. And we have, our bodies are this pretty complicated system of many interdependent parts. I think there are sort of two forces that go on. One is the interdependent parts really depend on each other. The other is, in a sense, many of those parts have a certain universality to them. So if you take one part away, other parts will be able to compensate and sort of fill in the function that you need from that part. And it doesn't always happen that way, but it's something where those are sort of two counterbalancing forces, that everything is interdependent, yet any one thing can be sort of filled in from other things in many cases. So I think in terms of what evolved away, I mean, a famous thing is we don't have tails anymore. We have kind of a bone at the base of our spine that's kind of like where the tail might have attached, but there ain't no tail there anymore. And that's an example. Now, presumably, if our distant ancestors were hung out in trees a lot, it's good to have a tail if you're swinging from tree branch to tree branch. Tails are really an important thing in arranging for you to keep balance and so on. But in us, us sort of boring bipeds that don't spend a lot of time swinging from tree branch to tree branch, at least most of us don't, the tail is something that wasn't so important. And I don't know why, generally, evolution does tend to simplify things. If the tail is really unnecessary, the tail might cause trouble. It might get, it might get infected. It might get jammed somewhere. It might be something that some predator can catch hold of or whatever. It might be inconvenient for one reason or another to have a tail. And so gradually, if you really don't need the tail, the fitter organisms will not have the tail, and the tail will gradually disappear in the population. Let's see. Oh my, there are questions here that get quite philosophical. Let's see. It's a question from Icy here. Is science getting harder? Are ideas getting harder to find? I don't think so. I think the doing of science as a profession is in some ways easier and in some ways harder. But the process of solving problems in science, I would say, is definitely not getting harder, and in some ways is getting easier. Why do I say that? So you might say, people have been doing science for hundreds of years, maybe even thousands of years. Haven't all the easy questions been answered? Well, what happens is, once one set of questions get answered, they become the building blocks for sort of building out something where you can now answer new questions. The things that were sort of the difficult questions of long ago become the things we take for granted today, and the things that we are kind of standing on to reach new questions today. And so I think if anything, the kind of the waterfront of, I don't know, I'm wondering, is it the case that there's a sort of a broader range of areas that have now been opened up to the point where we can ask questions about them than there were in the past? I'm not sure. I think it's probably stayed almost the same. But I think what happens is that in any given area of science, there will be a set of foundational questions. There'll be work done on those. Maybe they'll be answered. Maybe they won't be answered. Maybe some of them will be answered. There'll be a development, a building of that sort of tower of results in that particular area of science, and it gradually builds, and you kind of are, the new science that you're going to do is going to be at the top of that tower. Okay, so, but to us, in a sense, education is about kind of getting us to the point where we know about what's in the tower that's already been built. Research is about what's getting us to the next level of the tower, so to speak. And gradually, the education gets easier to do because well, for a couple of reasons. One, the concepts that get developed, when a concept is first developed, it's often developed in a rather complicated way because people didn't understand what was important about it. It's strangely similar to that code refactoring and that biological simplification I was just mentioning. It's sort of, you can get an idea, a concept, and it just manages to reach where you're talking about things, but it's really kind of difficult to explain, and there's no good description, there's no good word for this, and we've got 6 levels of definitions for that, and so on and so on and so on. And gradually, over the course of time, people understand what's important, and the whole thing gets simpler and simpler to the point where it's much more direct and easy to explain. So that's one force that makes things kind of get sort of easier to explain. Another thing that can happen is you can end up with a situation where at first you say, oh, we've got all these different creatures on the earth, and they all have different kinds of, one has a thing that sticks out that looks like this, another thing has a sticks out that looks like that, another one like this, and so on. And then we realize, actually, those are all kind of the same type of thing. Let's say they're all birds, and they've all got wings and beaks and things like this. And we don't have to sort of start talking about, oh, it's this beaky thing, and it's got this feature and that feature and the other. It's a beak. And that becomes sort of this abstract generalization that we can just say once, rather than having to say, there's this creature that has this, there's that creature that has this, and so on. And so it is with many areas of science that, and other things, that we end up having these sort of generalizations, these abstractions that we can kind of say once. Once we understand that generalization, we can kind of say it once and communicate it educationally just once, rather than having to go in and say, there's this case, and there's this case, and there's this case, and there's this case, all these things to remember. Another dynamic that makes sort of education easier is that the things that become part of everyday life get broader. There are things, I don't know, for instance, the way hyperlinks work on the web. Everybody's pretty familiar with the fact you click something, it's a link to something else. Well, the notion of graphs and networks, of there are things and they're linked to other things, and there's this whole network of links. That's something which, before there were things like hyperlinks, might be a little bit hard to explain. Now that people are used to this idea of links to links to links and so on, it's a lot easier. You have a basis for explaining that idea. So it becomes easier. It becomes something that's part of sort of everyday life. And so it becomes something you can kind of take as the base level and not have to go into a long explanation of it. So that sort of helps to make things easier to explain. And all of this helps to get it to the place where sort of through education, one has built this kind of platform of where science has reached so far. And then the question is, from that platform, how far is it to the next low-hanging fruit, so to speak? I mean, back when there was always nothing known in science, there were a certain number of obvious things that one could sort of reach in some metaphorical sense and get. But gradually, as science builds up and we know more and more, we're building this sort of taller and taller platform, this taller and taller tower. From the top of that tower, there's now new low-hanging fruit to get. Now, I have to say, one of the things that's been a feature of at least my efforts in science is that it's often the case that even when there's a field that has built a pretty big tower, there are still foundational questions that haven't been answered. They're sort of the most obvious, and some of the questions you guys ask here are sort of the obvious questions in some sense, they're good questions often about some particular area of science. And sometimes it's like you might ask that of somebody who knows that science well, and they would say, if they really know it well enough, they'll say, look, that answer is just not known. But other people who have been working in that science for a long time even will have never thought about that foundational question, because it's something that got sort of forgotten in the development of that science. And they'll usually, as a practical matter, they'll say, oh, of course somebody has answered that. Say, who's answered it? Where's it been answered? I say, well, somebody's answered it. I'm sure somebody's answered it. You dig a little further, and eventually they realize, that's really odd. Although that's a foundational and obvious question, nobody ever answered it. And so what can often happen, and it's sort of the story of some of the things I've done in science, is that as you've built some other tower, some other collection of tools, for example, particularly computational tools, you can say, oh, there's this foundation over here, was never answered. Let's go in with our new tools and let's see what we can do. And it often is the case that it's actually rather easy to answer that foundational question, which 50 or 100 years ago, when it was first formulated, those tools didn't exist. And that question was very hard to answer. And people gradually sort of ignored the question and just went on and looked at the things that they could answer. So that's a way in which there can be sort of hidden soft target, easy science, so to speak, that can nevertheless be very important. I would say that in terms of the institutional structure of science, it's gotten easier in the sense that it's much easier to get educated about science. There are many more venues to get educated about science. Even these little live streams that I do are an example of a kind of a way I hope to get a bit educated about science that sort of didn't exist in the past. But then when it's a question of the doing of science, if you're a professional scientist, there's a certain amount of overhead of sort of dealing with this large institutional structure of kind of all the sort of bureaucracy of the way that science operates and the way that people write academic papers, and they have sort of, are you going to publish my paper or not, or how does this work, and does this paper have the right citations to this and that, and there's kind of a whole kind of bureaucratic structure that you have to kind of work through in order to do science as a professional scientist today. And that has almost nothing to do with the actual difficulty or not of solving the actual scientific problems. It just has to do with the fact that there's millions of scientists, literally, and there's kind of this kind of it's a complicated kind of human bureaucratic structure that maintains science, and so that can cause things to be more difficult. Zayden comments that the more we've learned that there's a lot more to learn. Yes and no. One of the things that happens is there'll be a field of science that defines itself in a certain way, and it has certain methods. And by golly, with those methods, it can hollow itself out. It can get everything that we got with those methods. In fact, often doesn't even take very long. It often takes a decade, 2 decades, something like that. And some area, once some method has developed, it's like we can solve everything that can be solved using that method. And sometimes people say the definition of that area of science is what can be solved with that method. And so then once that method has kind of scooped out everything that's there, you'd say, oh, there's nothing more to know. Now, what is being ignored in that is, well, that was what you got with a particular method. Even that same set of scientific questions, if approached with another method, you open up this whole new, giant, new, run of stuff to do. So it sometimes is the case. I mean, throughout history, people have been, there are all these quotations, and I kind of am amused because I hear these things for real, and people who have always laughed at them in the past. I mean, like in 1900, for example, I think there was a famous quote from the chap who ran the patent office in the US that said, everything useful that could be invented has now been invented. There were similar comments around that time. Everything interesting in science and physics has already been discovered. Well, that was obviously absurd, because in the light of history, the early 1900s was a period of great energy and expansion, for example, in physics. relativity, quantum mechanics, all these kinds of things suddenly came on the scene, and they suddenly opened up all these different areas. How do people end up saying sort of that there's nothing happening? In fact, a friend of mine who's a well-known venture capitalist is fond of saying that, look, innovation has slowed down. There's no innovation happening anymore. But I think what tends to happen is that each of those people are looking at innovation in a particular area. So it might be, there are no new sort of social media startups that are being created that are particularly notable. They all seem to be doing the same thing. There are no new, e-commerce startups or something. There are no new startup companies in a particular model of what a startup company is. That are, well, there are new ones, but they don't have sort of fundamental innovations in them. But so what tends to happen is people get confused because they'll look at a particular area and they'll say, this area is getting hollowed out. There's nothing much more to do in this area with the methods that we're doing, with the kind of thing you can do with the Silicon Valley startup of this kind and that kind, kind of all the things that were low-hanging fruit, easy pickings in that area have been picked. And so then it looks like, oh, if that's what you're focusing on, there's nothing more to do. But the point is that the structure of kind of knowledge tends to be that there's always something else out there, off in the out in a different place that where there is great innovation to be done. And what sometimes happens is there'll be innovation in some area, the area will get well worked out, and there will stop being so much innovation. And it's like, okay, that's all done. We don't have to do anything more there. Then there'll be some other area that's sort of some distance away. It will have lots of innovation. It will build a taller tower. And eventually that tower will come to affect that first area you were talking about. There's this kind of disruption that can happen, not from within, usually, not from within that area. That area has just been, and the particular methods that have been used, that's been worked through, and everything that can be done there has more or less been done. But when this other area with its other methods comes online, it can then go sort of attack that first area and often make kind of disruptive progress in that area. And this is something we see in industries and sciences and so on. It's one of the reasons when it comes to education and so on, it's one of the reasons why the more you know, the better off you are. Because if you just know that particular area, that particular methodology, it's like, okay, but that's all been worked out. And the real progress is going to come from somewhere else. And so you have to kind of know what you know has to span these different areas for it to be possible for you to make progress. Because if you're just focused on that one first area, you're never going to make very much progress. Another thing that tends to happen is people sometimes say, oh, you want to do this area, you should just study this thing, just study that one tower. And you'll get, the more you study that one tower, the taller you'll get, the further you'll get up that one tower. And that is okay if you just want to lay sort of one brick on the top of that tower. If you really want to reach significantly further, you're almost certainly going to have to get something from another tower. And I think that and what you see often is even the place where there is the most innovation is sort of between the towers. There'll be two areas and they're both pretty well developed, but there's some interface between those areas, some interdisciplinary area which is something where those two things never collided before, so to speak, but now they are colliding. Now these two fields have relevance to each other, and that's where the innovation is going to happen. That's where the energetic innovation is possible, because it's essentially a newly exposed kind of methodology that one didn't have access to before. And so I think that's sort of a common dynamic is that there's this tower, it gets developed to a certain point, then there'll be some other tower, it gets developed, then there's this kind of this empty space between them, and then that sort of things start happening there, and then another tower gets built there, and so on. And that's at least a metaphorical picture of kind of the way that progress happens. And I'm fond of remarking that in different fields of science, for example, when they're well developed enough that there's a named university department, there's a collection of prizes named after that kind of science. By the time one is at that stage, the high innovation period of that science is over. Or at least if it isn't over, it's going to be another 100 years before kind of the things that were foundational before and were never solved in the foundations get to be accessible from tools from elsewhere. So that's kind of a sort of a picture of things. Oh, Paul is commenting, I think, in relation to my comment about how there's nothing more to be invented, that it's ironic that Albert Einstein started his revolution in physics while working in a patent office. It is important to fill in a little bit more of that history, because it's, often scientific history is very cartoonized. And, it's like, poor Einstein toiling away in the patent office and, didn't really know much, et cetera, et cetera, et cetera, and suddenly invents relativity, figures out the photoelectric effect, invents photons, all those kinds of things, and Brownian motion and all that, all in 1905. How could this be? Well, let's be realistic. Albert Einstein had gone and gotten a PhD in physics at, if not the top, one of the top couple of universities in the world at the time. It wasn't a particularly interesting PhD thesis, but he had gotten sort of the highest level of physics education that existed. What did he do? He did something that I would say, perhaps entrepreneurial people might do in today's world. He went to the then analog of Silicon Valley, which was the patent office in Bern, where, because at the time, and perhaps it's ironic that, yes, it was a time at which the US Examiner of Patents had said there's nothing new to be discovered, but there were a lot of patents being produced about things like refrigerators and all kinds of things like that, probably bicycles, things of that kind, that were very hot at the time. Ironic for refrigerators, I suppose. But in any case, so this idea that it's kind of like the from nowhere comes these theories of physics, not to reduce the importance. I think the thing about what Einstein did, and this is more a historical point, the thing that is interesting, it relates to this whole thing about towers of science and so on. In physics, there was a big tower that had been built around differential equations and mathematical physics and this and that, and a big technical tower that was pretty complicated. And then there were these effects that in the end would need relativity. And what Einstein did in his original paper on relativity is he just thought about conceptual experiments. What if you were taking a mirror and you were bouncing light off it and the mirror was going at half the speed of light? What would happen? These kinds of things. It's, in a sense, like a philosophy paper. It reads a little bit like the papers that people, or the things that people wrote in ancient Greek times, where they were trying to sort of reason their way through the way the world works. It wasn't something built on the great big tower that had been assembled in the physics of its time. It was something that came in using a different methodology and making use of certain experimental results, which were new, which had come into existence because of technology innovations. That was the reason that it was possible to make sort of a big jump forward, was that not because it was building brick by brick on this existing tower, but rather it was coming in and making having a foundational realization that came from outside of that kind of tower. Now, in our own efforts with our model of fundamental physics in the last few years, which I must say I view as being the next big step after what happened roughly 100 years ago with the creation of relativity and quantum mechanics and so on. I think that's a case where there's been a lot of technology built in physics, a lot of wonderful things done in it. But in fundamental physics, there's sort of a paradigmatic, a fundamentally different set of ideas that are needed to make progress now. And those are, I think we've been lucky enough to find those ideas, but where did they come from? They did not come out of the main line of development of physics as it's been done for the last 100 years. No, they came from ideas about computation that came from the side. Now, I myself have been sort of lucky enough to have done physics and computation. And so I guess I was the place where the sort of mixing of that set of ideas from what's known in physics and ideas that come from computation could sort of get mixed. And that's what made it possible to have kind of the step forward that we've been able to have with this sort of new approach to fundamental physics. And that's fairly typical. I think had I even stayed sort of doing physics as I did when I was a teenager and a little bit beyond, I'm quite certain that the physics project we've now done would never have happened, or at least wouldn't have happened under my sort of leadership, and it might not have happened for another 50 or 100 years. But it's basically because I've done lots of different things, which somehow one can use the ideas from those other things on the thing that one was on the original thing, rather than the sort of main line of progressive innovation. I mean, typically, as I say, when there are new methodologies, you've got 5 to 10 to 20 years. When that new methodology in some particular field is like really hot, you're figuring out lots of stuff. We've seen that with machine learning, for example, in the kind of computational area. A lot of stuff gets worked out in a period of 5 or 10 years, and then it's a slower story after that. And many other examples that can be given of that. And I think that's so. And then, as I say, it can be 50 or 100 years before you get the next shot in that particular area. Anyway, I should probably wrap up here in a moment, but yes, I think I need to go. But Parker is commenting here on predicting the future and what the future will be like. We'll talk about that another time. It's an interesting thing. I've had a solid 50-year span when I've been able to kind of make predictions and see what happened with them. And I would say one thing that's interesting is there are inexorable predictions about the future, things where I can just tell you, this is what's going to happen. It's like chug, 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 chug. That's how things are going to evolve. You can see the seeds of something, and you can see that over time, that thing will eventually become a big thing. Even some things I've built myself, I can see the inexorable future that, 50 years, 100 years, whatever, those seeds will have grown into big things. It'd be nice if it happened sooner, but might not. And then there are things where it's a big surprise, like just didn't expect that. And it's sort of an interesting interplay between the things which are the inexorable future and the things which are the surprises of the future. And sort of recognizing where there might be surprises is an interesting problem. I need to go and look at some things actually that are related a bit to building some of the future of computation. But I think I should wrap up here. And thanks for a lot of interesting questions and comments. And I look forward to doing this again, hopefully next week.